Well, thanks for the introduction. Hello, everyone. I'd like to thank you all for attending today. My name is Greg Vernon. I'm Director of Product Management at Coreform. And today I'm really excited to share with you today my presentation on Coreform IGA, how we're enabling commercial application of IGA. So just from an agenda standpoint, I'll talk about IGA at Coreform, kind of what our motivation is, and some of our core technologies and how we view building a commercial application for IGA. Also show a brief example of these tools and technologies coming together to solve a problem. And then also briefly mention some of our open source contributions that we're providing back to the field. A little bit about me. I spent about 8 years prior to Coreform working as a contractor for the U.S. Department of Energy, where my day job, my role was as an FEA analyst. And so I spent pretty much every day inside of CAE and CAD applications and solvers and peer review, trying to run analyses and get out results and then communicate those to customers that I had. And so I always like to think of IGA as being a business tool that makes businesses more efficient and more effective. And with that, I'll just segue into then our motivation for commercial IGA, which is very in line with that kind of vision. If you're a researcher in IGA, you're almost certainly familiar with this figure that Professor Hughes has shown before and talked about in his book about the workflow for a simulation analysis and the different steps are in there. If you're not a researcher, but you're an FEA or CFD practitioner, maybe you may not be familiar with this figure specifically, but the steps in here are probably pretty familiar to you. And the real main takeaway from this figure is that a majority of the time is spent in these non-value added steps to run a simulation. So you can see here, this study was from the early 2000s. The actual running of the simulation is only about 4%, but we're spending 75% of the time just trying to build the mesh and the steps that are involved with building a mesh. And then there's some other model preparation and then post-processing things. But as I mentioned, these are non-value added. As an analyst, I wish I could have just gone from a design solid model straight into a simulation, right? All these other things are just a means to an end. And so then really our motivation is of IGA and of Coreform is how do we drive these non-value added parts to effectively zero? And one of the ways we can do this is by decreasing the time to build a mesh. But if we can do this while also increasing the simulation accuracy through spline basis functions, we can actually result in an overall decrease in the time to the solution then. So if we've cut out all this non-value added things, we have even a little bit more flexibility that even if the simulation takes a little bit more time to run, overall, our total time to solution has decreased. And if we decrease total time to solution, that allows you to advance or accelerate your product design cycles, as well as lower your costs. So with the motivation discussed, I want to now talk about the building blocks of commercial IGA that we see at Coreform. So just like commercial FEA, commercial IGA requires these various technologies to work together and to be accessible to end users. And these form the pillars of a commercial IGA offering. The first of these is that you need to have a spline basis. And of course, a spline basis could be a traditional finite element basis, like a standard linear Lagrange polynomial or a quadratic Lagrange polynomial. Those are spline bases. Or they could be a NURBS or a T-spline or a U-spline. You then need to have a tool that can perform the mesh generation, which is essentially building the spline space for your problem. You then need to have numerical methods that can interpret the spline bases in your mesh and the kinds of physics you want to solve and can perform the integrations and solve contact and any kinds of constraints and load and boundary conditions that you have. But you then need to also have a solver that provides like an interface between the end user and the numerical methods. So it allows the end users to efficiently and effectively apply all these techniques to solve their real engineering problems. And if you've done these things, you then have built this commercial IGA offering. Now, I've left a few things out here that are also important to talk about, such as post-processing and some of the other model pre-processing things like attributing material models and stuff like that to a model. But those are kind of subsumed by some of these other problems. But those are other things that we do need to consider as well. And I will touch on those briefly later on today. Let's talk about then our spline basis. So at Coreform, we have developed a patent pending spline basis technology called U-splines. A little bit about U-splines. They are an unstructured spline basis that's capable of smoothly and accurately representing these complex CAD models. They're compatible with NURBS and T-splines. They also support local modification of cell size or element size, which is called H refinement, degree or P refinement, and then also intercell continuity, which we call theta refinement. And this includes things like T junctions. But in practice, we need to be able to have C0 at sharp edges and at other areas, and then we need to be able to have increased smoothness at other regions. They also are a locally supported complete positive basis. They form a partition of unity, and they're locally linearly independent. And also, as you can see on the right, we support these in both in 2D and 3D. So on the top figure here is an unstructured mesh layout on a surface. We're showing one of these C1 basis functions on that layout. And then the bottom is an unstructured U-spline on a volume that is maximally smooth. So it's C0 where there are sharp edges, C0 on extraordinary points, and to make sure that we've passed admissibility and we meet these requirements for the U-spline. But then elsewhere it's maximally smooth. So now on to mesh generation. At Coreform, we developed a world-class meshing software called Coreform Cubit, which we use to build our U-spline meshes as well as traditional FEA and CFD meshes. Coreform Cubit is a mature meshing software. It's been in development for nearly 40 years. It is a comprehensive tool for creating or producing hex meshes, as well as tetrahedral meshes, particle meshes, curves, surface and volume meshes, hybrid meshes, so like surface to volumes, mixed meshes, so to have a single volume that's got a mixture of tets, hexes, wedges, and hexes. And it's packed with more capabilities that can be discussed in this setting. But Coreform Cubit then serves as a perfect tool for us to build meshes and prepare IGA simulations, as well as we're working with a number of open source partners to also, and other third-party commercial solvers to use Cubit to pre-process and generate their meshes. Then on the numerical methods, we've developed a novel IGA method, which we call the Flex Representation Method, or FRM, which builds upon the powerful approximation capabilities of U-splines and our ability to then build those U-splines in Coreform Cubit. Now, I'm not going to go into a lot of depth on FRM, but I'll talk about it at a high level. It's very similar to a cut cell technique in which there's a physical domain that's immersed within some computational envelope domain. And then the portion of the computational domain that's not in the physical domain is what we call here the fictitious domain. We've got it in purple. However, U-splines allow us to build then these novel envelope domains that can partially fit to the physical domain, as we can see here at kind of the top right of the jelly bean. And that can increase the accuracy per degree of freedom in those regions. So if those are critical areas for your analysis or for your results that you're trying to process, you may want to have partial body fitting in those regions. Additionally, we can apply boundary conditions on elements on those conforming surfaces. So having a conforming boundary condition, which we can enforce weakly, as we just saw in the previous presentation, or previous presentations, we can weakly enforce these Dirichlet or other boundary conditions. We can also have immersed boundary conditions, which we can enforce weakly. And we can also have boundary conditions that kind of straddle both conforming and immersed regions. And lastly, we're then developing a solver called Coreform IGA, which natively implements our FRM flavor of IGA. And if we put these technologies together, we've enabled our users to design simulations that are tailored to their specific needs. So especially tailoring the total time to solution versus accuracy per degree of freedom. And so then this results in the spectrum of modeling approaches, which we call the flex spectrum. So on the left is a traditional FEA approach. Still, it's IGA in that we are using spline basis functions, but it's using a traditional FEA approach where we're doing a body-fitted hex mesh. And as you might be able to see on the right, where we have a traditional immersed or traditional finite cell method, the physical domain has some complexities that make it very difficult to build a conforming hex mesh on. And so traditional FEA approaches often will defeature just so we can build a hex mesh. And so even though it's IGA in that it's using spline basis functions, we've really broken the vision of IGA of using the same CAD model and not have to have this model pre-processing when we do things with traditional IGA methods. But what we can do with Coreform IGA and with the flex method is we can have partially body-fitted computational domains where we relax the constraint in local regions of conforming to the geometry that make it easier to build a hex mesh, but limit the immersion to just certain regions. We still get all the power of not having, accuracy per degree of freedom by having body-fitted meshes elsewhere, but then the ease of being able to build a mesh by relaxing those tough constraints. Additionally, you can even go even further and say maybe you only want to fit the major features of the geometry. So in this case, this quarter piston is effectively a quarter cylinder, and so we can immerse it in a quarter cylinder geometry. Now I'd like to show a little example of putting all these pieces together. So this problem is it's a cast iron C-frame that's loaded as shown in the idealized diagram at left, which is often how you might draw this on the back of a piece of paper or on the back of an envelope and do some kind of hand calculations. But in reality, in practice, we oftentimes receive CAD models that have a lot of extra features that maybe are required for manufacturing. So in this case, there are some small fillets that were added by the designer to reduce sharp hazards so that while during manufacturing, people aren't going to be cutting themselves on it and have, so this meets like OSHA requirements, as well as adding some fillets that reduce the stress concentrations. So I'm going to pre-process this model in Coreform Cubit. Now, I've sped this video up, but overall, this simulation or this process took about 5 minutes. So the first step is we're going to import our physical domain, our CAD geometry, and we're going to produce or design the computational domain. So I'm going to take some drastic defeaturing of my model here to create kind of a horseshoe shape that captures the general flow of that C-frame. I then assign that as my computational domain, and I've just now re-imported the physical domain. Now, I could just build a mesh there, but I wanted to show that you can do all the traditional FEA pre-processing techniques like web cutting and imprinting and merging to design your computational domain how you'd like. As you can see here, I might try to pause this real quick. Oops, missed it by just a hair. So we can see all of those small features are still present in the physical domain, but they are immersed by this bounding U-spline computational domain. So now, when we want to apply boundary conditions, as opposed to applying these to the mesh, we actually apply these directly onto the physical domain. And so here, what I'm doing is I'm going to create a couple of subsurfaces where I'm going to then be able to apply a uniform pressure. And what's important with this is that now we have decoupled the boundary conditions from the mesh that we're going to be creating. So in traditional FEA, again, we have to be applying boundary conditions. Oops, didn't mean to do that. We have to apply boundary conditions onto a conforming region of elements. As we can see here, as I zoom in, this finite element mesh or this computational domain does not have to actually conform to our surfaces. What this means is that we can actually change the boundaries and the shape and the size of our load regions without having to remesh. In traditional FEA, when you change your boundary conditions, you oftentimes have to remesh. And sometimes your meshing strategies that you had previously worked no longer work. So then just to recap what we did in that pre-processing, we took some physical domain without defeaturing. We immersed it in this computational domain, this background grid, so that we immerse the fine features of the model, and we'll recover those through adaptivity, adaptive quadrature, local refinement of U-splines. Um, but then we've generally captured the general shape of the part, which allows us to have higher accuracy per degree of freedom than if we had immersed this in a single large bounding box. And then validate this against traditional FEA. So here are the two results. At the time of this presentation, we only had the ability to export stresses at quadrature points. So our figure on the left, you're actually seeing the quadrature points. And so you can kind of notice some of the adaptive quadrature in some of the corners here, in some of these cut regions. But as you can see, these results are very close to each other. And to dig deeper, we even ran a mesh convergence study to compare these two results. As you can see, the Coreform result in the solid line at top is a cubic U-spline, and we quickly converged to the solution, while a traditional low-order HFEM technique hasn't even converged at over 1 million degrees of freedom. Whereas we've essentially converged by under about 100,000 degrees of freedom. And what's interesting is that even down here, with only a few thousand degrees of freedom, we have almost the same solution as we did with over 1 million degrees of freedom. And this really speaks to then the high approximation capabilities of spline basis functions. And just to review the motivation real quickly, we can see that we've simplified the model building for the hex meshes, which allows more engineers to go in and build these complex meshes for simulations. It reduces the labor cost, allowing you to run either more simulations for the same cost or have less cost for those same simulations. We've eliminated geometric errors, which is one of the primary sources of errors in simulations. There's obviously errors with materials and errors with physics and other things that are also large sources of error. But this at least eliminates one of these sources. And as we showed, we got these high accuracy results. We didn't sacrifice accuracy. We got these efficiently. And what we're saying is make your compute resources work smarter. Don't make them work harder. And then, of course, the goal is to then accelerate your design cycles. So I'll finish real quickly on how we're supporting open-source IGA. We're doing this by we're adding specification for Bezier extraction into the Exodus mesh format, which is an open-source format developed at Sandia and part of the open-source CCAS project. We've added Bezier elements to the VTK library, which forms the basis of ParaView, and that's available in ParaView 5.8 and newer. So I encourage you to go out and look at that. That's part of the standard now. We've also added support for Bezier extraction into libmesh. And libmesh then is the basis for the open source Moose finite element solver. And we're working with the Moose developers to then support this entire pipeline to get IGA simulations running in Moose. And with that, I'll mention if you want to learn more, you can visit our website, join our forum, or contact us to see how you can become an early adopter of Coreform IGA.